Hi everyone, I am Dr. Marwa bin Said-Romdhane from University of Tunis Al Manar. In the following 10 minutes, I will present you our study entitled PV System Inverter Control Design based on H-infinity control. The study has been performed within our research team KEHNA from Laboratory of Electrical Systems of INIT. The outline of my presentation will be as follows. First of all, I will give you the background and the motivation of this work. Then, I will present the system under study. The following parts will be dedicated to the proposed control, the weighting functions design with some simulation results. And finally, I will present the conclusion and the future works. Let's start with the background. Nowadays, photovoltaic systems have advanced to become one of the most trendy distributed energy systems, especially for residential applications. DC-AC converters present an essential element in this application. Proposed control strategies for these converters are very diversified in literature. However, since PV evokes specific requirements according to the singularity of residential loads and to local standards in relation with grid losses and grid impedance variation, H-infinity control presents a good candidate for this application. Indeed, it has the benefits of being robust even for grid fluctuation and load variation. However, the H-infinity control is characterized by its complexity, mainly to generate weighting functions and especially the weighting function W3, which is responsible for robustness of the system against parameters variations. In most cases, W3 is chosen as the first order function. Other papers use a second or third order function. In order to determine its coefficients, they used several methods such as the game theory, the practical swarm optimization, and the curve fitting method. This paper proposes a simple and systematic tuning method for the third weighting function. The system under study includes a PV system linked to a DC bus in parallel with the storage system. The interface between DC and AC bus is composed of a DC-AC converter. Single and three-phase linear and non-linear residential loads are connected to the AC bus. In this study, authors will focus only on the control of the DC-AC converter. The slide shows the main circuit of the LCL filter at the output of the DC-AC converter and its block diagram as well as the deduced transfer function. The goal of this slide is to fix an approximate variation range of the grid impedance, which can be determined based on the LCL filter resonance frequency. In fact, the relation between the grid impedance and the resonance frequency is given by the following equation. Based on this relation and the plot of LCL filter resonance frequency with respect to the grid impedance, the approximate variation range is 0 and 15 milliohms. The slide presents the control of the DC-AC converter based on H-infinity control, which is used to regulate the current at the output of the LCL filter. The goal of the H-infinity control is to tune a stabilizing controller K so that the H-infinity gain is less than gamma as shown in the first equation. Gamma is between 0 and the unit and indicates the level of optimality. The figure presents a typical H-infinity algorithm design with weighting function and nominal plant. The slide presents the flowchart of the H-infinity controller tuning. As shown in this flowchart, the first step consists in determining the system transfer function. After that, the first weighting function to be tuned is W1. Once this function was set, the weighting functions W2 and 3 can be determined successfully. It should be noted here that the weighting functions are determined based on the desired shapes of SR and T. The determination of the nominal plans and the weighting functions allows the creation of the H-infinity controller K. After that, the order of the H-infinity controller is reduced since the order of the obtained one is high. The last step of the H-infinity synthesizing is to check the norm of the closed-loop transfer function. If this norm is greater than 1, the choice of the weighting functions should be adjusted. For good reference tracking and disturbance rejection performance, W1 is fixed as a second-order low-pass filter. The first figure shows the influence of the damping ratio on the weighting function W1. It should be noted here that when the damping ratio tends to infinity, the obtained H-infinity algorithm has the same behavior as an ideal resonance controller as exposed in the second figure. The next step is the determination of the weighting function W2. To prevent the control signal from being too large, we assign to W2 a constant and small value. The next step after getting W1 and 2 is to set W3. This figure summarizes the different steps of the third weighting function W3. The frequency response of W3 has to ensure the following criteria. First, the gain of W3 should be greater than or equal to the maximum gain of the plant uncertainty. Second, in order to ensure that S and T are complementary, the crossover frequency of W3 must be sufficiently above the crossover frequency W1. And third, in order to satisfy conditions required by MATLAB mixed sign function, the gain of W3 should be smaller than 0 dB for frequencies below the crossover frequency of W1. In order to satisfy all these conditions, the following equations must be solved. Based on the obtained results, W3 must pass by points A, B, C, and D, as shown in the first figure. Based on MATLAB software, we can deduce the curve which passes through these points, which corresponds to W3. After fixing the weighting functions, an H-infinity controller K can be directly created by using mixed sign MATLAB software function with the defined G, W1, 2, and 3. The first figure shows the original and reduced H-infinity controller, and the second figure shows the dot plot of W1 and 3 and the obtained T and S. We move now to simulation results. This figure shows the grid current regulated based on the obtained reduced H-infinity controller K for LG varies from 0.1 millihenries to 15 millihenries at 0.1 second. As shown in this figure, the grid current is well regulated even for large grid impedance variation. This figure presents the grid current and its reference for a reference change from 5 ampere to 10 ampere. As presented in this figure, the H-infinity controller ensures a fast dynamic response. In order to show the robustness of the control against filter parameters variation, this figure presents the grid current and its reference for variation of 10% of the filter capacitor and the variation of 50% of the converter site inductance. We move now to conclusion and future works. The paper deals with PV system connected to grid for residential application. It presents an improved H-infinity control that ensures robust response to grid impedance variation and nonlinear load harmonic injection. The obtained simulation results validate the theoretical analysis ensure the robustness of the control against parameters variation. A partial approach is under development to validate experimentally the improved H-infinity control. And thank you for your attention.